Welcome to this presentation on PID controller design and verification. We will state the requirements on the controller. We will derive the closed loop characteristic polynomial phi. We will solve the Aryabhata's identity to design a controller. We will verify the controller in Scilab, and we will conclude with a discussion and homework. Here is the problem statement. We are supposed to control this plant, which has been obtained by sampling a continuous plant with a sampling time of 1 second. Here are the transient specifications for a step input. I want the steady state error to be less than or equal to 2%, rise time to be less than 15 seconds, overshoot to be less than 5%, and the settling time less than 50 seconds. From the transient requirements, let us determine phi. Let us start with the rise time. N is given by rise time by Ts. Recall this variable from one of the earlier lectures, and this is 15 because rise time was 15 seconds divided by 1 second, you get 15, and from this recall the condition on omega. Omega equals pi by 2n, which is pi by 30, which is 0.1047. The next is the overshoot constraint. The condition is given here. This also we derived earlier. When I substitute for epsilon 0.05, omega is 0.1047 divided by pi, it becomes 0.905. We will choose rho to be equal to 0.905. The desired closed loop poles are at rho epsilon plus minus j omega. This comes from the error model that we used earlier. So the desired closed loop characteristic polynomial is given by phi CL of z. This is the symbol that we used. It is given by the factor on the right hand side. When I simplify it, I get this expression, and when I substitute for rho and omega, I get this equation, the one in blue. You will have to remember this. In fact, I will ask you to write this down. Let us calculate the control law next. Let the plant G and the controller GC be given here, ratios of polynomials in Z. From that we can determine the closed loop transfer function, and the denominator is 1 plus GGC, which becomes 1 plus BSC by ARC after substituting from here, which becomes ARC plus BSC divided by ARC. Now we require ARC plus BSC to be equal to the closed loop characteristic polynomial that we derived in the previous slide. We want a controller with integral mode because we want to reject steps. So we require that RC equals delta R1 as per the internal model principle. So we will solve the last equation where we have replaced RC with delta R1. We want to solve this equation. Recall the characteristic polynomial that we derived 2 slides ago. Recall that the plant is given by this transfer function. Now let us solve the equation A delta R1 plus BSC equals phi CL. While solving this, note the unknowns and the known values. The plant is given by B and A, so A and B are known. Phi is also known because that comes from transient specifications. But notice that delta also is known. Delta is part of the controller, that is the integral mode. So what we will do is we will group A and delta as known quantity, So in this equation A delta is known, B is known, phi is known, we need to calculate R1 and SC. When we calculate this equation, we obtain R1 to be equal to this and SC equals this polynomial in Z inverse. So how did we solve this? That is using Aryabhata's identity. We will show the details of the theory behind Aryabhata's identity in the next video. For now, we will use Scilab code to solve this equation. We will see the Scilab code shortly. So here is R1, here is SC, and GC is given by SC by RC or SC by delta R1. Let us substitute SC from here, and in the denominator we write delta times R1. When I multiply this out, I get this controller. It can be implemented directly or as a PID controller. Here is the Scilab code. Recall that the plant transfer function is given by B by A. Here is B and here is A, and here are the degrees given for these polynomials, and we have delta as 1 minus Z inverse, its degree is 1. As I mentioned earlier, we multiplied A and delta and then use that to solve the Aryabhata's identity. That equation is xd plus yn equals c. So I have implemented this as a Scilab function x dy nc dot sci. At this point the controller is calculated. We know R1 and SC, and RC is given by R1 into delta. But in the rest of the code we will just verify that the solution that we get is indeed correct. We multiply R1 and A nu. A nu is nothing but A into delta, and then the second term on the left hand side of Aryabhata's identity was SC into B. We multiply these two, we add these two polynomials, and we have to check when we add this whether we get the right hand side, which is the closed loop characteristic polynomial. And of course we get the expression for RC by multiplying R1 and delta. You should always remember to include the diary statement which writes all the output into this file, and you have to remember to close this diary. So here is the Scilab output. The values are self explanatory. Remember, this is phi. When I solve this, I get SC to be about 2.5 minus 2.5 Z inverse plus Z power minus 2, and R1 is 1 minus 0.0909 Z inverse. So I get SC and R1. Now I verify, multiply these, multiply the second term BSC term, add these two. When I add this, I get 1 minus 1.8 Z inverse plus 0.819 Z to the power minus 2, and these terms are 0, 10 power minus 17 and 10 power minus 18. So we can ignore these, and this is the same as the phi that we had obtained earlier, and RC is obtained like this. So these are the values that I had used in a previous slide. Here I have implemented using xcos. It is in this file with extension zcos. When it is simulated, I get this response to a step input. The overshoot condition of 5% is met. Settling time of less than 50 seconds is also met. It is between 45 and 50 seconds here. The steady state error is 0, so the offset condition also is met, but the rise time condition is not met. We wanted it to be 15 seconds, here it is little more than 20 seconds. So let us summarize. Overshoot requirement is met, settling time requirement is also met, but the rise time requirement is not met. Further tuning is required to meet this requirement. We will explain this while designing pole placement controller in a future lecture. We can implement this directly as PID controller also. Recall the controller that we derived. We can implement this through this PID controller. This is the PID controller with filtering and SC equals TC. This is the discrete time equivalent. We derived this in one of the earlier lectures. As a homework, I would want you to calculate K, tau I, tau D and capital N. I would also want you to carry out simulations using the PID form of the controller and continuous time plant model. With this, I have come to the end of this presentation. Thanks for joining. Goodbye.